Hello everyone. As I mentioned in my previous video, there are two important proofs in solid mechanics that I skipped for this video, so let's get to them. The first one is, why is the stress tensor symmetric? In other words, the tau yx, if you look at the 2D case, is the same as tau xy, huh? So is there any reason these two are the same? The answer is yes. If you look at this 2D element here, and we neglect the changes in the elements, so assume that it's just like at a small local point, so the changes are very negligible, then we can show this easily by taking moment about the single point on this element. So if I take some of the moments about this point here, right? So I take some of the moment about that point, let's call it point A. So I take some of the moments about point A in any direction, doesn't matter, let's say counterclockwise. What would you get? Well, these two sigma x's would cancel each other. They both have the same arm, which is dy over 2. The same goes for these two sigma y's. They again both share the same length dx. They are collinear. So those will cancel each other, okay? They will not have a total net moment. This tyx and this txy pass through the point, so they will have no effect whatsoever as well. The only thing remaining that we have to count is this one and this one. Okay, and if you consider this to be a simple square element, so both elements are the same, so let's say dx and dx, or d and d, or delta and delta, whatever you want to call it, or a and a, then the total moment here is tau yx is clockwise, so it's going to be negative tau yx times a. Tau xy is positive, so it's going to be positive tau xy times a. And this has to be 0, otherwise the element will spin, and we don't want any spin. We want pure static equilibrium, and clearly from here you can see that these two have to be the same. Done. As simple as that. So these two have to be the same. And the other thing is the direction of these shear stresses, just so you remember, this is the x-axis, this is the y-axis. So on this surface, where the normal to the surface is positive x-axis, tau xy is basically in a direction that is tangent to this plane and in the positive y direction, so it is upward. For this one, similarly, for this face, where the normal is y and the direction of this one is positive x, so this is the positive direction to the right. Now for these two faces at the bottom and on the left, that's a different story, because here if you look at this element, the normal to it is in the negative y direction, so the positive shear on this one is in the negative x, because the normal is negative y, so the positive components means the direction should be negative x, as you can see. And similarly for this one, you can see that the direction of the normal is negative x, so positive direction for shear should be in the negative y direction. Okay, that's why you see these two are this way and those two are converging to the other corner. Okay, so this is about the first proof. The second one is a little bit more interesting, and that was the relation between E, G, and nu. If you remember, I showed you several times that G is equal to E over 2 times 1 plus nu, or if you cross multiply, E is equal to 2G times 1 plus nu. Where does this come from? Okay, these three important constants are related to each other, but how? And if you look at the internet, surprisingly, there are not a ton of good proofs on this. One place that I found a good proof, and I borrowed my picture from that, is this website. The picture on that is really good, so I would rather directly use that, and again, the credit goes to these people, not to me. So here I have the same element, A and A, and I consider a case of loading which is pure shear stress. So I assume tau and tau on this side, and then tau and tau on the other side. And remember, they are equal. Okay, so in this case, I assume that tau xy and yx, they are the same, and they are both equal to tau. All of it. No normal stress, just shear stress. Okay? Now, what I want to calculate is how much this direction, this diagonal direction, will change its size. What is the change in the length in this direction? Let's first find out how much the diagonal will increase in size. So here we fix this bottom portion here, and we apply tau on the other side, so we get this total basically shear strain on this angle or on this angle, and that is equal to gamma. So this whole angle is gamma. And again, this bottom surface, we consider it like fixed. And then what? And then, so this corner here, this corner that was here, is now going to go to there. And so the new diagonal is going to be this one. And the question is, how much is this distance from here to here? This distance is gamma times A, assuming that gamma is very small. If you look at this right triangle, this side is A, this is gamma, and gamma is a small angle, so gamma is the same as tangent of gamma because it's a small angle. And so this is going to be A times gamma. Okay? Now, if you look at, there is another triangle up here. If you look at this triangle, this dimension here, from here to here, this dimension, which is actually the difference between the final length of the diagonal minus the initial length, and this is that initial length. So this one and this one, these two red ones, are the same. So this increase in length is going to be that gamma A, correct, times what? Times cosine of 45. And this angle is 45. It's the angle of the diagonal. So gamma A cosine 45 is the change in the diagonal length. And how much is the original length of the diagonal? Well, if it's A and A, diagonal is square root 2 times A. So this is the original diagonal. This is D naught. So delta D over D naught, or strain in the diagonal, is going to be gamma A over cosine 45 over square root 2A. This A and this A would cancel. And then cosine 45, as you know, is square root 2 over 2. So if you simplify this, this squares would cancel. This 2 comes to the denominator. This gamma stays, so it's going to be gamma over 2. So gamma over 2 is the strain on the diagonal. On the other hand, remember that gamma is equal to tau over g. That's what we know from the Hooke's law. So if I plug it right here, then the strain on the diagonal is going to be tau over 2g. Okay, so on the left side, you can easily see that the stress we found on the diagonal, the strain we found on the diagonal, is tau over 2g. So far, so good. Now, we are going to look at this picture, this diagram that we have on the left. We are going to look at it in a different way and try to find the strain on a diagonal in a different way. So we say that if you look at this, what is really happening? If you look at this, the main diagonal is increasing in length, or not the main diagonal, one of the diagonals from the bottom left to the top right. And this other diagonal, if I can connect them with the line, this one is shrinking in length, right? So I can say that since this diagonal is shrinking in length and the other one is stretching, it's like grabbing these two corners and pulling them, while on these two corners, I'm compressing them. Okay, and this is what you can see here on this right side. The question is, with how much? With how much of the stress you are going to extend them? And the answer is, it should be the same as these taus to have equivalent effect. So these two that stretch this way and this way, they should be tau. These two should be negative tau. Is that correct? Well, all you need is to decompose. If you decompose, would you get something, similar to the original one? Well, let's take a look. So this one is going to be this and this. This one is going to be this and this. This one, these two, and this one, these two. Correct? Now if you look here, clearly these two would cancel each other and these two would cancel each other. Yes? But if you look here, these two will be added and these two will be added. Right? Or if you want to bring them on the surfaces, correct? You can do a similar thing as well here. So here, if you go on these two surfaces and look at it, if you look at these two surfaces, you can say that basically on this left surface, what do I have? On this left surface, these two would cancel each other. These two would stay and they will be added, so you're going to get this component. On this top surface, look, again, these two verticals would cancel, these two would stay, so you're going to get this one. On this right side, these two, if you look at them, the horizontal ones would cancel each other, the vertical ones stay, so you get this. And on this bottom one, again, the verticals would cancel, the horizontals both to the left, you get this. Okay, so I can see these two cases are equivalent to each other. Whether you use this left one or this right one, whatever result you get should be the same. The loads are equivalent. Now the question is, how much is the strain on the diagonal on this right side picture? So on the left side, that's this much. What about the right side? Well, on the right side, in this direction, whatever this direction is, you have tension. And the amount of the stress in this direction, the normal stress in this direction is tau. So tau divided by E is going to be epsilon in that direction, okay? And that is exactly this one, sigma 1 over E. That is the axial strength in that direction. Now, in this normal direction to that direction, in the normal to this diagonal, in this direction, your sigma 2 is negative tau, it's compressive, and so the normal strain in this direction is sigma 2 over E. And you know that if you have in one direction some strain in the normal to it, which is in this case this main diagonal, in this one direction, there will be a component of the two direction, and these two are related through negative nu. So this is the result of strain in the two direction. This is the result of strain in the one direction, but both of them added together in the one direction. And sigma 1 is tau and sigma 2 is negative tau. So if you replace, you're going to get this, simplify, and you're going to get basically, as you can see, T over E, which is tau over E, which is common, times 1 plus nu. Now, both of these terms are strain on the diagonal, and if they are the same, what would you get? Well, the taus cancel out. The 1 over nu, 1 plus nu over E should be the same as 1 over 2G, and clearly that means E equals 2G over 1 plus nu, or if you find G is going to be E over 2 times 1 plus nu. So you clearly see that from this strain on the diagonal on these two equivalent loading, we can find this very important proof, this one, and also by taking moment about the corner, we showed the other one. So hopefully this video was useful to you, and I'm gonna see you in the next lecture.